All right, guys, back at it, week 5. Okay, so we're going to spend this weekend, my guess is probably this weekend, next week, looking at this method of integrating using partial fractions. Okay, and it helps us with rational functions sometimes. Okay, so if you have a fraction made up of polynomials, sometimes this works out. Doesn't work out all the time, obviously, just like any other method of integration. So it's really kind of cool. If you take something like this, where let's suppose we, had 14 over 15. Well, we know the prime factors of 15 are 3 and 5. So we could take this guy, and what partial fraction decomposition allows us to do is to write this fraction as a sum of 2 or more other fractions with denominators that are the prime factors of the original denominator. So this 14 over 15 can somehow be written as some number over 5 plus some number over 3. Okay, and it allows us to take this guy, okay, and break it into a sum of fractions where these denominators are prime factors of the original guy. Okay, now this is actually relatively easy to do. So if you take this 14 over 15 and we say, okay, it's got to be equal to some number over 5 plus some number over 3. Okay, now how about if I multiply this whole thing by 15? Okay, so I would get 14 equals, let's see, the 5 cancels the 5 here, so it'd be 3a plus right here, the 3 cancels the 3 here, it'd be 5b. Okay, so any ordered pair of numbers that would satisfy this equation, and obviously there's a whole bunch of them if you let a and b be both integers and rational numbers, okay, you get a whole bunch of solutions here, okay, where, okay, it's some a and b paired up as an ordered pair, okay? So figuring out what a and b are really important. Okay, this guy is actually pretty easy to do, I'll be honest with you, if we assume that a and b, we want integers. Okay, notice you would get, this would work out when a equals 3, okay, and b equals 1, because obviously that would give you 9 plus 5, which obviously is 14. So in this instance, if we say, okay, a and b have to be integers, okay, you would end up with the solution 3, 1, okay? But there's no reason that a and b have to be integers. A and b could be, any numbers whatsoever as long as they satisfy this guy, okay? Well, the same thing happens, okay, with polynomials. Let's suppose we had, this guy where it's 1 over x squared plus 15x plus 50. Well, we could break this denominator down into its prime factors, okay, by factoring it. So you would have x plus 5 times x plus 10. Okay, so this guy can be expressed as a sum of 2 fractions where one fraction has one prime factor and the other fraction has the other prime factor as their denominators, and then it's going to have to be some constant a and some constant b. Okay, so you can see how this method would be really helpful in integration. Okay, so we're going to look at some relatively simple ones today, okay, and we'll work our way up, okay, throughout the week and into next week, okay, but this notion of taking a fraction and decomposing it, breaking it down, okay, into a sum of simpler fractions, okay, that we can integrate, okay? All right, so let's see. This first guy right here, okay, is a relatively simple one. Okay, we'll get through 2 simple ones today. Okay, so this guy right here. Okay, first things first. Okay, I'm going to pull this guy out as a constant multiplier. Okay, 1 over. And then I'm going to factor this quadratic down here, so that would give me x plus 3 and x minus 2 dx. Okay, so all I'm going to do for the time being is just work on this guy right here. Just work on finding a way to decompose this guy. Okay, so let's see. I have 1 over x plus 3 and x minus 2. Okay, so that has to be equal to the sum of a fraction where I have some constant over one of those prime factors plus some constant over the other prime factor, x minus 2, like this, okay? All right, so we say, okay, what do we do here? Well, how about if we multiply this entire thing all the way through, okay, by x plus 3 times x minus 2. And in doing so, notice we're going to get rid of all the denominators. Okay, so all these fractions here in this equation will become something that's not a fraction. Okay, all right, so when I multiply this by this whole thing, notice the numerator here cancels with the denominator here, so you just get 1 equals. All right, now notice when I multiply this guy by this fraction, notice the x plus 2's cancel, or I'm sorry, the x plus 3's cancel off, and I'm left with just x minus 2 times a. Okay, so a times x minus 2 plus, okay, right here, notice the x minus 2's will cancel, so I'll be left with x plus 3 times b. Okay, b times x plus 3. Okay, now I need to find any ordered pair of numbers, okay, that will satisfy this guy. So we can choose random values for x, okay, and solve for a and b, okay? All right, so let's see. How about if I choose something that makes this whole term go away? And so then I would just have 1 equal to this guy, and then I could solve for b. So what if I let x equal 2? So if x equals 2, okay, notice I'll get the 1 here equals a times 0 plus b times, notice that if I put 2 in there, that's going to be b times 5. Okay, so notice what happens here is this drops out, and I solve for b by dividing both sides by 5, so I just get b equals 1/5. Okay, all right, so I have something for b. So how about if we do this? If we say, okay, let's make sure a stays there, but b goes away. So why not let x equal -3? Okay, so when we do that, we get 1 equals a, well, if x is -3, -3 minus 2 is -5, plus b, if x is -3, then that's 0. And notice that b drops out, okay? So I get 1 equals a times -5, and then divide both sides by -5, so I'd get a equals -1/5. Okay, now this works out algebraically. Now I'm going to check this guy. I'm going to check this guy, and this is the only time I'm going to check, okay, to show you this works out. Okay, so if I go back up here, okay, and I take this 1 over x plus 3 times x minus 2 equals a. Well, a is -1/5 over x plus 3 plus b, okay, b is 1/5 over x minus 2. Now all I got to do is show that this right-hand side is equal to the left-hand side, and I've figured out how to do it. So you figure right here, okay, I'm going to have to multiply above and below by x minus 2, x minus 2, x minus 2, and right here I'd have to multiply by x plus 3, x plus 3, x plus 3. Okay, so let's see what happens here. So up here, I'm going to get a negative 1/5 x plus 2/5 all over x plus 3 and x minus 2 plus right here I'm going to get 1/5 x plus 3/5 all over x minus 2 and x plus 3 equals, let's see, when I add them together, what happens? Okay, I've got an x plus 3 and an x minus 2. Okay, so notice that this guy right here cancels off with this guy, and I get 2/5 plus 3/5, which is 5/5, which is 1. Okay, and see what I got? Okay, so I know this is what I'm looking for. These two guys, okay, which are going to give me these two guys right here. Okay, so let's see. All right, so we're going back up, and let's see, let's get this set up. So I've got this guy right here, 1 over x plus 3 and x minus 2 dx. That's equal to 5 times the integral of, let's see, I split this up where I had an x plus 3 plus and an x minus 2 right there. Okay, let me go down and get my a and b. So let's see, my a is negative 1/5 and my b is 1/5 right there. Okay, so this is the guy I have to work with. Okay, so let's see. I'm going to split this up into two integrals, and notice I'm going to pull this out as a constant multiplier. Okay, so negative 1/5 times 5 is just negative 1, so I get the opposite of 1 over x plus 3 dx plus, notice when I take this integral and put it here and I pull this out as a constant multiplier, to have 5 times 1/5 was just 1. So I get 1 over x minus 2 dx. And guys, notice how everything's coming out real clean. This is not always going to happen. Okay, when you get into some of the more difficult ones, it's nowhere near as clean as this. Okay, so let's see. I got to integrate this guy and I got to integrate that guy. And don't forget about this negative sign here. If you lose that guy, you're going to get the wrong answer. So I'm thinking, how about we use u substitution here? So how about if I say u is x plus 3, then my du is dx. Okay, so I get the opposite of 1 over u du. Well, when we integrate 1 over u du, we get the natural log of u. So this is the opposite of the natural log of u, which will end up giving me the opposite of the natural log of x plus 3. Okay, so now I got to do the same thing over here. We let u equal x minus 2, so du is dx. So I get the integral of 1 over u du, which gives me the natural log of u, okay, which will give me the natural log of x minus 2. And then we have our constant of integration. Okay, so we're done with the integrating, so now it's just a matter of can we put this in a simpler form, the answer. Okay, numerically we're correct, okay, but you know, I'm looking at this and I'm saying, okay, I have an addition between two logs with the same base, so I should be able to use the product rule here. Now this negative sign is really important. When I bring that back, I get natural log of x plus 3 to the negative first power, which gives me the natural log of 1 over x plus 3 plus the natural log of x minus 2 plus c. And so when we use the product rule, a sum of two natural logs is the product of these two guys. Okay, so we get the natural log of this guy times this guy. So I would get x minus 2 all over x plus 3 plus my constant of integration. And that right there is certainly simpler than what we had up here. Okay, so when you get to this point, numerically you're correct, but we want to keep working on condensing things if it's possible. Okay, so that's the first one down. Okay, let's see what we got with the second one. Okay, very similar type problem. Okay, let's see. I'm going to pull that 10 out front. Okay, so I get 1 over. I got to factor this guy, so it looks like I'm going to get x minus 3 and x minus 7 dx. Okay, so I have to work on decomposing this guy. Okay, all right, so that's what I have to do first. Okay, so I take this 1 over x minus 3 times x minus 7. So that's equal to some constant a over x minus 3 plus some constant b over x minus 7. Okay, just like the first one, let's get rid of all the denominators, okay, so that we're not working with fractions. So I'd have to multiply through by x minus 3 times x minus 7. Okay, so when I multiply that by this guy, I just get 1. Okay, when I multiply this by this guy, the x minus 3's cancel off, so I get x minus 7 times a. And when I multiply this guy by this guy, the x minus 7's cancel off, so I get the x minus 3 times b. Okay, so this is the point where we can arbitrarily, choose some value of x that's going to make our life simpler. So let's suppose we choose x equals 7, and in doing so, notice this is going to cancel off. All right, it's going to go away because 7 minus 7 is 0. So I would get 1 equals a times 0 plus b, 7 minus 3 is 4. So notice this goes away, divide both sides by 4, so I get b equals 1/4. Okay. Now, how about we get this guy to cancel off? So we choose x equals 3. Okay, so I get 1 equals a times, let's see, 3 minus 7 is negative 4. Okay, plus b times 3 minus 3 is 0. So this cancels off. So I'm left here, divide by negative 4, so I get a equals negative 1/4. Okay. All right, so let's see. Let's pull down another piece of paper, and because I don't have enough room here, and let's get what we need. Okay, so let's see. All right, I have this 10. Okay, and we have 1 over this x minus 3, x minus 7 dx. Okay, so that's going to be 10 times the integral of something over x minus 3 dx plus 10 times the integral of something over x minus 7 dx. And let's see, what did I do? I put the a over x minus 3, so the a is negative 1/4. I put the b over x minus 7, and the b is 1/4. So we got everything we need there. Okay, so let's see. Okay, this is a constant multiplier, so I'm going to pull it out front. So 10 times a negative 1/4 gives me a negative 5/2. And I'd be left with 1 over x minus 3 dx. Plus, pull the 1/4 out, multiplied by the 10, so 10/4 goes down to 5/2. So 5/2 times the integral of 1 over x minus 7 dx. Okay, so from here on out, it's pretty straightforward. Use substitution. So right here, we let u be x minus 3, so my du is dx. So I'm going to get a negative 5/2 times the integral of 1 over u du, which gives me a negative 5/2 times the natural log of u, which is x minus 3. Okay. All right, so over here we do the same thing. U is equal to x minus 7. So my du is dx. Okay, so we get plus 5/2 times the integral of 1 over u du, which gives me 5/2 times the natural log of u, which in this case is x minus 7, plus a constant of integration. Okay, let's see what happens here. Okay, so let's see. This would be the natural log of taking this guy back. It's negative, okay? So that would be 1 over x minus 3 to the positive 5/2 power, okay? Plus bringing this guy, that's natural log of x minus 7 to the 5/2 power plus c. Okay, using my product rule, this gives me the natural log of, let's see, this guy would go up above, okay, and I'm going to take a look at, let's see, that would be the square root of x minus 7 to the 5th power, okay, which obviously isn't in simplest radical form. I'm going to do that. This guy would go down below, so that would be the square root of x minus 3 to the 5th power. Sorry, guys, plus c. Okay, so we've condensed it. Now all I'm going to do is just put this in simplest radical form. So let's see, natural log of. Okay, so let's see. I would take x minus 7 to the 4th power and take the square root. So I'd get x minus 7 squared times the square root of x minus 7. Okay, I think I'm running out of lead here, guys. Okay, hopefully I can make it to the end. Okay, so let's see. I would take the x minus 3 to the 4th power and take the square root, so that would be x minus 3 squared times the square root of x minus 3 plus c. Okay, and again, you know, starting right here, numerically, we're in good shape, but we can condense things, okay? So I would say that this guy would be a good representation of your answer. I like that guy the most. I could see maybe somebody saying, well, okay, don't put it in root form, just leave it in exponential form. And so they might do something, they might just leave it like this. Let's see what this looks like. Natural log of x minus 7 to the 5/2 all over x minus 3 to the 5/2. Okay, they might do something like that. Okay, you might have a professor in college that would let you do that, so that's maybe okay. Okay, what else could we do? Well, they're both square roots, so you might have something like this. Natural log of, let's see, square root of, that would be x minus 7 to the 5th over x minus 3 to the 5th, like this. Okay, so again, you know, maybe something that a professor would be okay with, and I'm thinking maybe one more. Natural log of the square root of, how about this whole thing to the 5th power? Okay, so x minus 7 all over x minus 3 to the 5th power. Okay, so there's some other possible forms of your answer. Okay, I know I'm partial to the one that we originally came up with right here. I'd be partial to this guy. Okay, but these are some possibilities. Okay, you know, it just depends, like I've told you many times. Okay, who's in front of the room. Okay, I'm looking at him right here, and I'm thinking I like this guy the best because it's in simplest radical form. But other than him, I kind of like this guy. Okay, because I'm comparing this to this, and it looks to me like this guy is simpler. Okay, that'll wrap it up for today. So hopefully that helps you out. We'll look at some other guys, other problems tomorrow. Miss all of you a whole bunch.